Good morning, everyone. So I have the pleasure to introduce George Froudakis, the speaker for today's event, that is going to give a lecture about gas adsorption that meets deep learning. And I would like to thank the international visit program of the Institute that has funded the travel and the seminar of today. And before we start the seminar, I would like to introduce the speaker. He is a physicist. He finished the bachelor and PhD in physics in University of Patras. The PhD was co-shared between Patras and Bonn University. And later, in 2000, he became assistant professor in the University of Crete, and now he's a full professor. For 4 years, he has been the head of the Department of Chemistry. He's one of the founding members of the Greek Institute of Research and Innovation. He's founding member of the Hydrogen Platform, the Greek Hydrogen Platform. And he has supervised 10 PhD students. Among of them, half of them have got the permanent positions either as university professor in US or abroad, and I'm happy to be one of them. And he has almost 200 publications. And I have the honor to introduce George Froudakis, and who is going to give the lecture. The floor is all yours.
Thank you, Andreas. Thank you for the kind invitation. It's actually my first time in Madrid, and I really enjoy to meet a lot of friends. I'm very proud of being here, visiting my former PhD student that have a very successful career here. So, and I would like to thank also the program that have funded this trip. So today I will speak a little bit about what we are doing recently, the last 5-6 years, that have to do with AI. Generally, in my group, we are focused in two of the main problems that humanity will face the next year, and this is energy and environment. How we do this? We do simulate porous materials, that in the pores of this material you can accommodate useful gases, like for example hydrogen, methane, that address the energy problem, or harmful gases like CO2, H2S, that have to do with the environment. And we are doing theory, we are modeling materials. And modeling means that we try to model materials like this. This is a metal organic framework, this is a real image. Good for us, these materials are periodic, so you can go down and see the structure, the periodic structure of the material. But in this structure, you can go to the scale, to the unit cell. The problem is that since we are talking about gas absorption, we are talking about weak interactions, physisorption. And in order to investigate this, you need to go to the scale of the molecules and apply very accurate quantum chemistry techniques. So then you can go to the upper scale that consists of the unit cell and use some DFT and build some classical interatomic potentials that allow you to go to the scale of the thousands of atoms and do some classical simulation like molecular dynamics and Monte Carlo. And if this breaking down of the system and constructing up of the method work properly, only then you can say that you can simulate a material. Since I will talk a lot about MOFs, I will use 3 slides just to make an introduction to the people that they don't know. The story of MOFs started from Omar Yagi in 2003, and this is from his first paper in Science. They are porous materials, periodic, that consist of building blocks that have metal cluster and organic linkers, metal organic frameworks. The yellow sphere that you see many times is just empty space. And since there is a big variety of metal clusters and organic linkers. The family of MOF now have something like more than 1 million structures. Some of them have been synthesized, some other have been just designed in theory. What is the interesting thing about this material that many people are working, and there is a great possibility that Omar Yagi will receive the Nobel Prize for this. If you take just a gram of this material and you open the surface area of this material of just 1 gram, you can cover the area of a football court. So they have a large surface. And this allows us to use them as for many applications like gas absorption. If, for example, you fill up a tank with this material, then like a sponge, it can attract gases and accommodate more gas than a lot of empty tanks. So it's very important applications, but also they can use it in catalysis, in many other different, also in biological systems for drug delivery, etc. So try to investigate these guys with the traditional techniques as I described before. It's quite painful. And this is one of our first publication of in the PhD of Andreas here, that he found out that if we put lithium ions in this material, we can increase the interaction of gases, of hydrogen actually, that it was that time a very important gas, and increase the interaction and store more hydrogen in this material. And actually that was the case. If you put in the organic linker these alkoxide groups, the hydrogen is interact with 3 times more binding energy than in the original MOF. And you can see here in Monte Carlo simulation, on the left side is the MOF synthesized by Yagi. On the right hand side is the one that was modified by Andreas, and you can see the difference in hydrogen storage. And the thing is that this was published early in 2008, and there were 2 experimental groups afterwards that came, one of Omar Farha here and Joseph Hub, that Omar Farha has now one of the biggest companies that produced MOF in US. And they follow our procedure, you can see here in the graphical abstract of this paper, and find out that they can accommodate a lot of hydrogen. And even then it was this paper of Martin Hartmann in Germany that he says in his graphical abstract, moreover, the significant increase in hydrogen absorption predicted by Andreas Mavrodonakis is observed. So they followed our procedure, and finally we managed to, and this I think is one of the success of theory, that you make a prediction and then experiments come to verify your prediction. Another success story was this one of COFs. Omar Yagi synthesized this COF 102 in 2007, but by that time he couldn't have enough material to put it in the porosimeter. So we did some calculations and we find the isotherms of this material 1 year later, and 1 year after the theory, the experiment came and verified the theoretical prediction. And you can see here the similarity in these 2 plots, and this is theory, this is experiment, and here the theory came 1 year before the experiment. So these traditional methods of multi-scale modeling of materials work fine, but there is a but. These calculations, the same as Andreas' calculations, took almost a year. So in order to simulate accurately one material, you need several months at least. And this is a problem, because now we are coming in the years of AI. And as you can see here, the artificial intelligence in chemistry, material science, and physics, these are the published papers per year. And you can see that after around 2000, it's rapidly going up. So how the thing started? According to my opinion, this is the beginning of everything, when IBM Deep Blue defeated Garry Kasparov in 1997. And the thing is that 1 year before, 1996, Kasparov beat the computer. So the IBM technician took the computer back, reprogrammed it, and then they managed to win Kasparov. Afterwards, nobody else won the computer again. For the computer, it's quite similar, and for a chess match, to understand how it's working, how the computer is working. So in every incident of the game, the computer can think all the possible answers and make a move, and then to each of these answers, all the different answers that the opponent can make, and then all the difference again, and make a very huge tree, a decision tree, and follow the branch that have the greatest possibility of winning. Another milestone in AI was the DARPA challenge. This challenge was in the US, when the DARPA said that a self-driving vehicle should pass Mojave Desert and make 150 miles off-road in the desert. The first year that this challenge was made, in 2004, there was no success. Nobody managed to finish the race, no car. And the furthest distance they made was only 7 miles. But 1 year later, only 1 year later, there was 40 finalists. So 40 vehicles managed to pass the desert, and this Stanley robot from Stanford University was the first one. You can see cameras and everything, and using a program that rolling trajectories can drive the vehicle. So in the first year there was a failure again. In the second it was a success, a great success, and nowadays there are self-driving cars everywhere, and I just heard that there is a self-driving bus in your university, and so I mean they are everywhere. They live among us. So I will close this introduction to have this picture for the students. It's from Oscar ceremony in 2014. So probably you can recognize these guys here. But the thing is, this picture, I didn't download it for a magazine of movies, but from MIT Technology Review, because it say how well the cameras that we have in our mobile phone can recognize faces. So this is also a great success of AI. AI is everywhere, and everybody is using it. So let's go to science now. This is a recent paper from Omar Yagi, and that he is using ChatGPT. ChatGPT to synthesize material, synthesize MOF. So instead of having a student trying to find ways that you can synthesize material, you can use ChatGPT, find all the different text that they're talking about the synthesis, and then do some searching and tuning, and then at the end find you a synthetic way. So Omar Yagi, the next Nobel Prize winner, a hardcore experimentalist, is using in his lab ChatGPT. So we are moving now to an area that we can call material informatics. Bioinformatics is something we know for many years, but material informatics is something new. In order to use AI, in order to predict properties of material, we need to build a database, then to develop an algorithm, because all these algorithms are based in data, to train our system and to make some predictions. So it's a mixture of computer science and material chemistry. The traditional programming that we're using for many years use data and equation in order the computer will find a property. But machine learning, it's the other way around. You have data and a property, and the computer will find you the equations. So how this schematically works in MOFs, in materials. So we have a database of MOFs. We need data. And a property that we are interested in. So for example, hydrogen storage, CO2 storage. Then we have to identify several important parameters for this property. For example, the building blocks, the organic, the inorganic, the topology, functionality. And we put everything in a matrix, and then we train our network, and at the end we can do some predictions. What are important things in this story? The quality of the descriptors, the size and quality of the data set, and of course the training algorithm. So talking about the descriptors, the quality of the descriptors, in the literature, they use mostly physical and chemical descriptors. This means the metal corners, organic leaking, but also the void fraction, the density, etc. We wanted to have some descriptors that that can be transformed in different kinds of materials that are in a way universal. And we thought about the atom types. The atom types, it's a very old story in chemistry. They use it in classical potentials in order to simulate the interactions between different atoms and molecules. The idea behind atom types is that atoms in molecules, they don't behave the same way. So for example, the carbon atom, it's completely different if it's participate in a benzene ring, or if it's in a carbon dioxide, or in a graphene. So the different types actually show the chemical behavior. And if we put inside the algorithms the atom types, we can impose the chemical intuition. And you can see here, this is when we studying methane absorption in MOFs using physical descriptors, chemical, and atom types. This is the error, and this is how we increase the training set. And you can see that physical and chemical descriptors are quite high, the error, while if you use atom types, the error is dropping very rapidly when you increase the training set. And it is worth to notice that combining the atom types with the best descriptors in the literature, in order to get the same accuracy, you need an order of magnitude less materials in your training set. So you save a lot of time. And since these atom types are actually something that based in chemical intuition is universal, so you can train in MOFs and predict it in different other materials like in COFs. Another important thing is the size and the quality of data set. In MOFs now there are many different data sets available. One was the Crete database from Cambridge that have experimental ready MOFs, and then the QMOF that use some MOFs that are optimized from this with quantum methods from the database. So there are a lot of databases. The problem is that each database have significant problems. And as you can see in this paper that just appeared it's not published yet, it's in ChemArchive, from Tom Wu, that is working in this field, you can see that there are significant errors in all of databases. And here, for example, in Crete, that there are MOFs that they are actually experimentally synthesized, you can see that 46% have problems. So it's very difficult to work with data that they don't have. This is an ongoing problem in MOFs. So we thought that since there are a lot of databases and many predictions, we need to have a tool that can tell us if a hypothetical MOF can be synthesized or not, because there are millions of hypothetical MOFs. And what we have thought is the following. If the experimentalists want to make a MOF, what they're doing, they put a metal cluster that actually the metal cluster define the topology and some organic linker. If the organic linker can take the corners of the metals and can coordinate it, you can make a MOF. Otherwise, you cannot make a MOF, a crystal structure. So sometimes these organic linkers, in order to catch the different metals, they deform. And this deformation is energy cost. And if this deform is a lot, then you don't have a lot of possibility to make the MOF. But if it fits perfectly, then it's easier to make the MOF. So what we thought is work reverse engineering. We take a MOF, a hypothetical MOF, we extract the organic linker, and then we optimize it and find the free form of the organic linker. And then we compare these two structures. If the energy and the geometry are similar or quite close, means that the MOF was not deformed a lot to make the MOF. Otherwise, it will need to deform a lot, and this cannot work properly. So this you can see three different database. The tobacco, that's a hypothetical MOF. You can see the energy and the mean square displacement, that a lot of red things means a lot of deformation. The core MOF, that's an experimental database, it's a better picture, more to the green. And QMOF, that are optimized structures with quantum chemistry methods, most of them are in the region that can be synthesized. And this program, this paper was just published in Chemical Information and Modeling, and the code is available. Actually, we have a web program that you can put your MOF and can tell you how possible it is to be synthesized. If you thought of a structure, if you find the structure theoretically, this program can help. And if you find something, because it's just we just released this, the MOF synth, if you find any problem, please contact me to correct it. Another important thing is how to use AI, and what is the difference between the AI that they use in banks and in supermarkets and in different databases. In material science, we are interested about top performing material. In the rest of cases, they want to have a global picture of their data. So we thought about an algorithm that we call it self-consistent machine learning algorithm that will identify only the top performing material. We are not interested for the rest. How this is working? Let's suppose that we have here some hundreds of thousands of MOFs and methane absorption, and this is the correct value of the MOFs and of methane absorption. How machine learning is working the traditional way? So we identify 100 of MOFs, we calculate with a Monte Carlo simulation the gas absorption, and then we use the training, this data to train the ML and to make a prediction. And let's say that the prediction is this red line. Then we do it with 200 MOFs, and then we do it with 300 MOFs and 400 MOFs until it stops. And this is the way that we use it up to now. What we propose now, we start with the 100 MOFs, again, randomly selected. We calculate with Grand Canonical Monte Carlo the properties, and we fit the line. And up to here, the two methodologies are exactly the same. Then we predict the 100 top performing materials. Maybe this prediction is not correct yet, but we try to find here. And we calculate the gas properties of these materials that they live up there, and we try to simulate again the absorption curve. This means that we don't care about what is going on in this area, but we concentrate here in top performing material. And we do this as many times as the 100 top performing materials are not changing. So we have a consistency. The machine learning method is giving the 100 top performing materials, and if we put these on the training set, these are giving the same algorithm. And you can see in this way we don't work in this part of the curve, but we can simulate correctly the top performing material that were actually interesting. So how this work in reality? Here we have ML predictions, Monte Carlo results, and if we use our algorithm, our algorithm finds 76 of the 100 real top performing materials by using 300 MOFs for the training set. If we use 300 MOFs randomly in the training set, we can identify only 4 of the 100 top performing materials. Say it in another way, because this is working in different materials, different conditions, a general algorithm. So in order to identify 100 top performing material, we use our algorithm, and with a training set of 261 MOF, we managed to find the 70 of the 100 top performing. In order to find this with the traditional method of randomly selected, we need 3,400 as a training. So 1 order of magnitude lower. And the same story is in COVs and things like that. Okay, let's go now to more recent stuff, like deep learning. What's the difference between deep learning and machine learning? Machine learning have an input, some materials or whatever. The user have to make future extraction and then can do some classification and find some properties like hydrogen, CO2 storage. The difference with deep learning is that the features extraction is made by the program. We use some neural networks here, and we have only to put the input data. So we save a lot of time and effort from the people, but what's the penalty we have to pay? Deep learning methods are data hungry. You need a lot of data. So I will tell you 2 stories about deep learning. The first one is we thought what will be the best, the absolute descriptor from a material that for gas absorption and general interaction. It will be the potential energy surface of the material. The potential energy surface, it's actually a 3-dimensional object that is saying it's combining the classical world and the quantum world, because you have the structure there, but you have also the interactions in all the space from the gas to the material. The problem is that we are talking about a descriptor that is a 3-dimensional object. It's a 3-dimensional picture. How can we work with this? The problem has been solved from our people in computer science with the convolutional neural networks that they used a lot in recognition of image recognition and also speech recognition. So you can put in these networks the input of picture, and then actually it can classify if it's a horse, a zebra, or whatever. And this can be made also in speech. So the input can be 2-dimensional, like it's here, or 1-dimensional, or many-dimensional, or 3-dimensional. So what can we put here are potential energy surface. potential energy surface that we can break it in small parts that we call voxel from V, the volume, as it was pixel in image recognition. So we have the voxels, and of course at the end we are interested in gas absorption. So let's see how this will go. You need two steps. One is to make the voxelized potential energy surface. So you take a material, the MOF, you make a two-dimensional grid, three-dimensional grid, and in each point of this grid you calculate the interactions with the material. And then in every you can color this grid by the interaction. So in our case, we use the 25 by 25 by 25 grid for our material, and to be fast, we use the Lennard-Jones classical potential to calculate the interaction and get this potential energy surface. But in the accuracy limit, you can make the interaction as the dimensions as much as you can want, and also you can use ab initio methods to calculate the interaction. Then, because as I said, these methods are data hungry, we need to do a data augmentation. It's quite typical in deep learning. So we take this potential energy surface and we make rotation, reflection, and flipping in order to increase the number of our data. So we do 12 transformation, and we have 33 input MOFs. So immediately we end up in 384,000 of input to use for training. Here is an example how this data augmentation works. You can see here increasing of training size and R square, that actually means the accuracy. And you can see this is without data augmentation and this is with data augmentation. You can see that with data augmentation, even though that you take the same image and you change it, it helps a lot. And it's helped a lot because we don't have so many data, and this is saving some time. What are the convolutional neural network? You can see here in a image recognition that the convolutional neural networks start from an image, make different, you can see parts of this image, and then make some convolutions and combine them to an eye, nose, ear, and at the end identify the tiger. Something similar we will do for the MOFs. We will take this, and at the end it will be like that. This is the schematic diagram of our algorithm that we take the voxelized potential energy surface. The neural network will get the future maps, and then we'll do convolution and pooling in order to decrease the dimensions and get some output like the gas updates. And if we try to look inside the computer how this procedure is working, we start from IRM of 1, and this is a picture. So here this is how the algorithm is going, and these are two-dimensional pictures of these three-dimensional objects in order to see how the procedure is going. And you can see in the beginning that you can recognize that we are talking about a MOF, so they're quite similar images, but at the end you go to a computer, only you are deep in the matrix. You cannot recognize anything, only the computer can recognize this. How this is working? CO2 absorption in Ottawa database of 300,000 MOFs. This is the training size, this is the accuracy, this is the geometric descriptors as used in the literature. This is the potential energy surface. You can see we can have an increased accuracy, and also in order to get the same accuracy that you need 30,000 MOFs for training. With our algorithm, you need only 300. 2 orders of magnitude less data. And of course, the same thing can happen in different kind of gases and materials. This is independent of this one, and you can see that the picture is similar. And imagine also that we used a small amount for training set, but with data augmentation, this database can go to 3.5 million of structures if you do data augmentation. You have a lot of data. So this is the first example that I show you. And now we'll go to the second. We were discussing with our collaborators from Toyota that were working for many years in this kind of project. And they told us they are using, they're working in the AI team of Toyota, they're working with images and image recognition and automatic driving and things like that. So, of course, for us that were physicists or chemists, potential and surface data is something that is very important for us. It's something, but for them, it's you do calculations that we don't need. Get only data. Nothing. Don't do any pre-processing. Use only data. This is the future of deep learning. So we followed this way, and we used a point cloud of the structure. A point cloud. What is a point cloud? A point cloud, you can see it's a cloud. It's again a three-dimensional object, but have points where the material exists, and you can see here a mug. Oops, sorry. You can see here a mug, a table, a car, and of course you can also each point you can color it of some properties, etc. How this is look a point cloud of a material, you can see here 3 different MOFs, very famous one, the RMOF1, the first that was synthesized by Omar Yagi. This is QBTC and UIO66, very famous MOFs, and you can see here the point clouds. So we build a new algorithm that actually take a point cloud and go to this architecture called PointNet and get some gas absorption. For us, the point cloud are the XYZ coordinates of the material plus the atomic number of the material. And of course, then it's done a lot of processing to get the output. This is how the structure look in the beginning. This is the RMOF1. This is the point cloud of the structure as it really looks. And before training, you can see that the neural network cannot identify all the atoms as important. But after training, you can see that the structure is actually like the original point cloud. And this is what we can do. You can see here some results. These are typical machine learning pictures. Ground truth, the property, ML prediction is everything. If everything is near the diagonal, means it's good. If it's not near the diagonal, it's not so good. So this is geometrical descriptors of predicting CO2. This is with point clouds. You can see it's much more condensed to the diameter, so it's more accurate. Here we used 90% of our training data for training and the rest for validation. And of course, different gases, different material, you can see a similar picture. So let's try to put all this together. Here we have the R square, that is actually saying the quality of the methods. Training set, and we have geometric descriptors with random forest method, point clouds and the potential energy surface with voxels. Without data augmentation, with data augmentation. So you can see to this limit, of course, everything, all the other methods overpass the state of the art in the literature that is using geometrical descriptor, but the point clouds are a lot down than the potential surface. The things, of course, change when we go to real big data. If we're talking about training size of hundreds of atoms, you can see the geometrical descriptors and the point clouds that overpass all the other methods. The thing is, these lines here are dot because we made an extrapolation of this line since it was not easy to calculate the potential energy surface for hundreds of thousands of materials. Because this method needs a pre-calculation of the potential energy surface. This actually needs only the structure, these two. So this is how the things are going when we have a lot of data and so these are the two different pictures that I described today. Descriptor-based deep learning that actually need less training data, but you need to make a calculation and your input actually needs something like 5 seconds to calculate a potential energy surface with a classical force field. This is the descriptor-free methods, point clouds, but actually the penalty is you need more data, but it's a faster input. You need just 5 milliseconds to calculate your input. And these are these two codes are available if you want to use them. The Moxel and AI adsorb in the GitHub of our group. So, coming back, this paper, this is a quite recent paper, 1 year before, talking about an autonomous laboratory for synthesis of novel material. Here they did almost everything. They use AI to screen databases and find properties and propose new materials. And then they use an autonomous lab to synthesize this material. And then to characterize them, and that was a great success. The only problem was that they made a serious mistake in the characterization of the material. So this article came in Chemistry World, new analysis raised doubt over autonomous lab material, etc. So this story reminds me all the examples I'm using of AI. First year they fail, and then it's something that everybody is using. And I think AI now, it will be the future of not only of theory, as we discussed for some years, but also from experiment. The problem is that I found this picture in the internet. This is scatter plots, this is informations. The knowledge is how you connect the information in your mind. Experience is how you will use this information to do something new. Strategy is to find the correct path to go to this one. And intuition is to go from here to there without actually passing all the intermediate step. The ML is actually erasing all the different parts. You need data, and then it will produce you something. So, no deep knowledge of in science will be needed, and this is quite dangerous. But Can you stop the progress? Kasparov beat Deep Blue in just one move. Turn off the button. You cannot go back, and the progress is always leading us. So, I would like to thank, first of all, my group. This is Mike, that is actually here. He's doing now a PhD in Madrid. This is Harris, that doing the code, the analysis for hydrogen and of synthesability of materials. Adonis here is the deep learning guy. You can understand it from his look. And Electra is working desalination, something that is quite serious in Crete, but also in Spain, I think. And the rest of the people of my group, there are several European projects that we participate. Of course, great support from Toyota, with my collaborator Konstantinos Gagas, and a lot of discussion and collaboration with experimentalists that they are synthesized MOF, like Pantelis in my lab. And all this algorithm, you can find it there. And with this picture, I would like to thank you and thank you for the kind invitation. This is a picture from Crete. Crete, except from nice beaches, it's a small island, but have very high mountains. Psilorid is almost 2,500 meters high and have snow all around the year. And last but not least, we're expecting you, all the people that are working in MOFs, in almost a year from now, in Heraklion, that the EuroMOF will take place. So thank you very much, and I will be very happy to answer any question, and I will be here some days if somebody wants to meet me and discuss with me. Thank you.
Thank you for this excellent talk. We are now open to questions. Who would like to?
Hi, so thank you so much for it was very nice, very inspiring talk. Okay, so I am an experimentalist, so I'm gonna share with you my concerns. So I always wonder about this machine learning. What can we do? How can we apply machine learning in our research when we work with new applications? Like, for me, the concern is the data sets, right? The numbers for me, for an experimentalist, they look huge, like 300. We don't have. CO2 capture is something, it has been there for many years. So now, how can we apply? What is your opinion about machine learning applied to new properties, like capture of water pollutants? Or so, how far are we from that? Or what is your recommendation? Yes. How can we accelerate the application of machine learning?
Thank you, Anna. You know, you are sharing my thoughts also. This is the problem. The problem is here where, for us, it's good for the theoreticians. It's good to work here because it's a big playground. We have all these millions of hypothetical MOFs and things that we can train algorithms and play with them. The problem is what you will find at the end. Can we find a new structure? Can we identify something completely new? What we are thinking and what we are working right now is to do inverse design. So how we can use machine learning not to screen materials, because screening is quite easy, but to design materials. And this will be the challenge of the next years. How somebody can identify a problem, like what you said, CO2 or water or pollutants, and design materials use AI to design materials for this specific application. And that will be this will be a challenge, and maybe I will come next year to talk to you about this. Hopefully.
Thank you very much. It was an excellent and a very interesting talk. I mean, following in the path of the previous question, maybe I think you were referring essentially, without saying the words, generative AI, right? I mean, the question, the big challenge now, as I understand it, is okay, it's all very well to use AI to quickly evaluate the potential for a given trial material as whether it's good or not for whatever the problem is, absorbing hydrogen or methane or whatever it is. The question is, how can we use AI to really propose new competitive structures, new materials that are better than the ones that we already know about, right? So, and I think there the great challenge is how can we take advantage of new developments in the field of AI, in particular generative machine learning, to invent new structures for us, new materials. So sorry, it was not really a question, but more a comment.
This is actually the task we are working right now. So up to now we use this for screening, and there are a lot of methods developed for screening that you can use it or you can improve them or whatever. The thing is generative algorithms, and this is the big challenge now, right now, as exactly as you said, and I think many researchers are working to this. And this will be a real success of AI, a real success. Up to now, we have produced different numbers, but screening with AI was something new for many years in different other categories of materials, in biology, biochemistry, things like that. With MOFs, we have an advantage that we are talking about a simple system. MOFs are simple because they're building blocks, they're periodic, so it's quite simple. So, and the thing is how you can predict some new materials, or what should we do with this data that we have, the databases that they have. Most of them have a lot of problems, and we learn our system with these databases. We end up in materials that cannot be synthesized. So I think that will be a big challenge if somebody can make a real, valid, good database for MOFs.
Thanks. And finally, a question of detail. I didn't quite understand what you were referring to when you spoke of atom types. So obviously you mean something a bit more refined than purely the atomic number defining the chemical species, right? So you are identifying different species of carbon atoms in different environments, I guess, right?
Yes, exactly. This is something typical for the people that are doing theory and simulation, because all the classical potentials that they use, the Leonard Jones, the Amber, all the classical potential, they work with atom types. It started from Karplus when they developed the charm classical potentials many years ago, and they saw that instead of talking about atom numbers, we use atom types. So for carbon, there are 3 or 4 different atom types. Carbon in a benzene ring, carbon in a CO2, carbon. And for hydrogen, for oxygen, if the oxygen is bridge, if it's a hydroxyl group, it's completely different. The behavior of the atoms in molecules is according to the environment. So this was identified in atom types. So that's why they have now automatic algorithms that you can take a structure, a molecule, and they define the atom types out of this, because it's used many years in classical potentials. All the molecular dynamics and Monte Carlo simulations that have been done in molecules and materials, they use atom types. So the idea here was to transfer this in machine learning. And that was why that was published in JAX, because people, you know, they really liked this idea of atom types, that you have the chemistry, the chemical intuition inside.
So I have a question. So right at the end, you presented a slide about the cost of the machine learning with descriptors and without descriptors. With the descriptors, we need a lot of time to get a point, but then we use less points to make the machine learning.
Yes.
But then with the descriptor free, each point takes very few time, but we need much more. At the end, did you do a calculations how many resources are you using with these two different approaches, or which one eventually is it cheaper? Because is simulation time is also disk is computer time, like CPU time, processors, and also you need a lot of storage to store this data. So did you make an estimation which one is cheaper or more expensive?
The thing, this, you are referring to this picture, the cheaper is the descriptor free, but there you have to have a lot of data. You have to have a lot of data. So at the end of the day, here, now we are somewhere here. But in the future we will go there. We will use just raw data, nothing else. And also, if you have a lot of data, you have another advantage that we didn't discuss it today. A lot of data are making auto-correction to the error. So for example, if you use ChatGPT in the internet, there are a lot of mistakes. But at the end, ChatGPT, they balance and they actually auto-correct these mistakes. If you have a lot of data, you can make corrections also. So they work like this. And of course, the new trend in MOVs also is to use programs like ChatGPT, large language models, to work also in MOVs.
I have a second question. So it's about the voxels. So if I understand correctly, we can consider that is a three-dimensional pixel, right?
Yes, exactly.
And then the third dimension is just the energy. Is it easy to implement another dimension, a fourth or even fifth?
Yes. Piece of cake. Because these convolutional neural networks are dimensional free. I mean, they work fine in one dimension, that is the speak recognition. They work fine in 2 dimensions, that's the image recognition. They work fine in 3 dimensions. They can work in 4 or 5. If you want, we can put some more dimension in this and try to see what is going on.
Yeah, because I was thinking on top of the energy, we could add another descriptor, for example, the electronic density or something more. I don't know then if it would accelerate, if it would help to reach this error, to reduce the error much faster, but then on the other hand, if it will make the simulation much slower.
Electronic density is something we're trying right now, but it's very slow. That's the problem. Then you're talking about at least semi-empirical or ab initio calculation, so it's completely in the other way around. The other thing that is sometimes they ask me is about this CO2 fingerprint of the AI. So, I mean, all these calculations have also a CO2 footprint. And if we are talking about big data and things like that, sometimes this will get important. And maybe in MOVs not so much, but all these use the computer and everybody that uses AI, I don't know.
Any more questions? Okay, so if no one has, so I would like to thank the speaker once more for coming here and giving this great talk.
Thank you very much.